Welcome everyone. It's very nice to see such large audience at such late time. It's 4 o'clock and weekend is coming, but it's good to that so many people join this presentation. So I will talk actually more about using deep learning based techniques to analyze some aspects of the football games, and there will be very little about football itself, unfortunately. So let's start. Basically, my name is Jacek Komorowski. I work in the startup company Sport Algorithmics that develop a system to analyze football videos, recordings of soccer games, and I also work as an assistant professor on Warsaw University of Technology. And basically, our aim is to build a system that will help to analyze videos or recordings of football games. It's intended for professional use, for soccer academies, for soccer clubs, and it's intended to help coaches, to help football analysts to analyze the soccer videos. Basically now the work of the football analysts that work in football academy or in club is quite cumbersome. He needs to manually watch all the games. If he wants, for example, to assess performance of certain player, he needs to watch all the game. He needs to look only at the parts when this player has contact with the ball and tag on this video only small fragments of the game where a certain player did some action, for example, yeah? And then he needs to prepare an assessment of his performance. We would like to automate the process. We would like to make a system that will track the players, track the ball, where we'll analyze the game and help to find all interesting aspects of the game, like find automatically situations where certain player possessed the ball, when he kicked the ball, when he shot at the goal. We would like also to automatically compute some statistics. For example, what distance did player run, or how fast did he run? On average, what was his maximum speed? Our assumption is also that makes the project much more difficult is to use off-the-shelf CCTV cameras. So we are not working on the video broadcast, TV broadcast, where these cameras have very high zoom and you can clearly see the entire player's body, you can see ball from the close distance. We would like to use the CCTV cameras installed around the playfield. So this is the, let's say, setup we are working on. We've got a number of fixed cameras installed around the playfield that basically capture part of the playfield from high distance, so we don't have a good zoom, and you would like to analyze the game. Unfortunately, yet there is no deep learning system that will do everything automatically. There is no big brain that will, take as an input the video sequence like that, and will automatically output all the necessary statistics, player tracks, and so on. You need to build it from smaller components. And in each component, you can use deep learning techniques to analyze part of the game, for part of the pipeline. So basically, the entire pipeline can be split into 3 phases. We've got this low-level processing, where we detect the ball, detect players, jersey, recognize number on players' shirts. There is mid-level processing, where we can track the ball in 3D, because using multiple cameras, we can track the ball in 3D. Tracking and identification of players, and also there is this high-level processing where we recognize aspects or interesting events in the game. Is this a pass? Is someone shooting at the goal? Was it a goal? And calculate statistics. In this talk, I will concentrate on a few aspects because it's not sufficient time to discuss every aspect of the processing. I will talk about ball and player detection, how we can efficiently do it, and about player tracking, how we can efficiently track players. These tasks, like ball detection, well, they seem easy for human. Yeah, okay, you watch the game and you see the ball, what's the problem? But to write a computer program that will do it automatically on such high-resolution videos, it's not so straightforward. First of all, the ball is not always circular, yeah? When it's kicked, you've got a motion blur, so it's like elliptical. Sometimes it can touch the line, Sometimes it can touch player's body, so you cannot just detect circles, because here you've got the ball touching the player. And sometimes you are not sure, is this a ball or is this a glove of the goalkeeper? Well, even human is not sure what it is. Detecting players, it's a bit easier because players are usually bigger, but also you've got a lot of these difficult situations, like two players can touch each other, and they can have unusual position, like falling or stumbling. So also you need to take care of such situation. And how did we approach this? Well, in terms of object detection, there are lots of generic purpose object detector already available. One of the most popular is this SSD300 object detector or YOLO object detector. And they are high quality, good performance, and they are suited to detect a large number of objects, like they can detect a dog, a cat, a duck, a car, or a plane. Like here I've got example, this detector, you can put an image, and it will give you the bounding box with probability that this object is a car, umbrella, person. Works quite good. But unfortunately for our purpose, it's not sufficient because this is a huge network. This is a huge network. It's got like 30 million parameters. It's got quite impressive performance, 60 frames per second, okay, more than real time, but on quite small images, 300 by 300. That's 900 pixels. And we are working on high resolution images that got 100 times more pixels. So performance of these generic object detectors is not sufficient. So basically, inspired by this design, we built something simpler that allows real-time processing of high-resolution videos and detect ball and player. The design looks like that. If you are interested in details, you can look for this paper, which is going to appear on the conference in 2020, but should be available in X-Archive, and how it works. Basically, as the input, we take an image. So we've got width, height, and 3 color channels, RGB. And the image goes through this is classical convolutional neural network architecture. Each of these blocks consists of 2 convolutional layers and max pooling. So it goes through these convolutional layers, and each of this block produces the feature map that's got half of the image resolution. The spatial resolution is decreased by half, and the number of channels is going up. So first block is creating the feature map that's got like width by 2, height by 2, and so on. I will talk about this part a little bit later. And then output from these feature maps is fed to the classifiers that classify, is there a ball? This is a ball classifier. It classifies, is there a ball on this particular part of the screen, which corresponds to this part. So we've got output feature map. It goes to the ball classifier, which is a simply convolutional network that outputs ball confidence map that's got spatial resolution 1/4 of the width, 1/4 of the height of the original image, and 1 channel, basically with value between 0 and 1. And it says, okay, 1 says there's high chance there is a ball in this place. 0, blue, says likely there is no ball here. The same with, and for player, for ball, we don't need a bounding box. The ball has the same object, the same shape almost. Yeah, it does not vary so much. Similar for the player. For the player, we take the feature map from the upper convolutional block, which produces feature map of the smaller feature map of the spatial dimension 1/16 of the original image, which also 1 means, or red means, there is high chance there is a player at this particular position, which corresponds to the spatial positions on the input image. Also, there is a regressor, also simply convolutional, consisting of 2 convolutional layers, that regresses bounding box of the players. So it regresses the position of the bounding box at the particular location. So this is classical convolutional network architecture, like VGG, nothing fancy, and why these bottom-up, top-down connections. This is based on this feature pyramid network concept, basically to improve the quality of the ball detector. Because if we don't have these top-down connections, the player detection will work, well, without any change. Because the player detection takes the input from takes the output from this block, goes to the player classifier, player regressor. But when we go down this channel, down this line, we add to the output of this convolutional block, we add the higher level features that got higher receptive field. And what it means? It means that the ball classifier does not look only on the small region around the ball, like 20 by 20 pixels, but it takes into account the bigger context. Without these connections, the ball classifier would only take into account a small patch in the image, like 20 by 20 pixels, which be more difficult to detect the ball. If something is round, okay, it's likely a ball, but it may be, something part of the advertisement near the playing field. Or maybe some marking, marking on the line or some jitter lying somewhere. But if we add this path, then we take bigger receptive field into account, and the classifier can make better decision because intuitively it can work take into account, is this round object? Yes. Is something, that's looking like a player's leg near? Yes. Okay, that's definitely a ball. But if this is something round, but it's not, but it's, around some stadium advertisement, it's likely not a ball. So this top-down path improves ball classifier performance. I won't discuss details on the loss function, how the network is trained, but basically just to give you a feeling how it's trained, it's fully supervised training. So basically what we did, and this was the most time-consuming task, we took like 8,000 video frames from real recordings and manually tagged the player position and manually tagged ball position in each of them. It was done by a couple of people, took like 2 or 3 months. But then we've got a large training set that we can train our model. And it was a classic stochastic gradient descent training, usual stuff with neural networks, yeah? We showed the input image, it was passed through the network gives us the prediction, and we know the ground truth. We've got the ball position and player's position marked, yeah, in our ground truth data. So we compared the outcome of the network with the ground truth, compute the loss, and then use gradient descent to minimize the loss. If someone is interested in details and how this loss function look like, you can look for the paper and see the details. And basically training of the network took like 2 days. And what are the results? I would say quite good. These are results on the publicly available data set. We use this in our paper. So you can see predictions from the network, 99% confidence that this is the player. This is also quite good. You can see here I've got this quite difficult situation, occlusion. The first player is detected with 99%, but okay, the network is sure that this is the player. The second one is occluded. We've got like 56 confidence. Okay, lower, yeah, because it's occluded, so the network is not sure if this is a player or not. Detection of the ball is much tougher, and because there are some objects like this marking that may look like a ball. So the network has lower confidence. So the confidence level in this example is like 22% only, but the ball is detected. Here as well, we've got unusual position. Oh, this one is lower. If the player is standing, the confidence is like 99% because that's the usual pose. The network was trained with the usual pose, but if the goalkeeper takes hands like that, well, during the training, network seldom seen the player having hands like that. So it's less confident that this is the player, but 80% is still quite high. In In terms of the numerical results, the usual quality measure of object detector is average precision or mean average precision. So basically this detector on publicly available Asia soccer data set got 90% ball detection accuracy, 94 player detection accuracy. If we don't use these top-down connections in detector, the ball detection goes down, by 5%. So adding these top-down connections in the network design helps with especially ball detection. With the player, it's almost the same, even it's better. But what's important, the network is very efficient. It can operate on these large high-definition images, 1920 by 1080 pixels, at almost 40 frames per second. So it's real-time, almost real-time. Whereas faster as CNN, it is a general-purpose object detector. Available in PyTorch, for example, you can use it and fine-tune it for your own purpose. It works fine as well, but it's much bigger. Number of parameters is like 100 times more, and it operates only 8 frames per second. So insufficient for real-time processing. And to see it in action, let me show. So here's some ball detection. We may see that from time to time, there are such red circles like on the foot on players, incorrect detections, and they happen. So we've got some additional post-processing steps to actually filter out these incorrect detections. Oh, like here, yeah. It's something circular near the player's feet, so it was classified as a ball. But there's next post-processing steps that get rid of such spurious detections. Oh, something's frozen. Okay, it doesn't want to play, so I will come back to the presentation. Okay, the next component I'd like to talk about is tracking of the players, because so far we detected only players, but it was separate detection, and each and every frame we've got a separate detection. These players were not linked. But what do we want to have is to have tracks of the player, to track each individual player through the game, how he moves. So we can calculate the statistics, the distance he ran, his speed. A very common approach to multi-object tracking is so-called tracking by detection. And it works like that. So we use this approach. It works like that we've got the current track of the object that we are tracking, like of the person. So these are the positions and appearance of the object tracked so far. Yeah? So we already tracked, like in 4 consecutive frames, we track a player. And then we've got detections from the new frame at time t+1. So we've got these detections and the new frame. And what we need to do is to match the track with the detection. Here is no-brainer, actually. Okay, we see someone is running here, and detections at time t+1 are like that. So of course, yeah, this is this guy. No other option, actually. These are blue, so definitely they are different. Sorry. This one, yeah, okay, dziękuję. Dziękuję. This one is white, but he is far away, yeah? So it's not possible that this one matches with this track. But in general, you may have much more difficult situations, like this one. When here, it's not so easy which one of these white guys is linked with this track, because we've got the white player running through this trajectory, and at time t+1, we've got 2 detections that more or less match to this trajectory. So that's the problem that needs to be solved in this multi-object tracking, that to match trajectories to detections. And you can have more difficult situation. Imagine, I don't know, free kick, when there are like maybe 5 or 10 players just, squeezing one near each other, and how we can track them in such rush. So basically the approach we take is like that. That we've got the targets, it means already tracks that we already know, tracks of, at previous timestamps, and we've got detections at a new time step. And we want to link these tracks with detections at a new timestamp. So what we do is we measure similarity between the track and the detection. If we go back, like here, the similarity is based, first of all, on the trajectory in the history, on the previous trajectory, and the position of the detection, because, okay, taking into account the trajectory and the position of the player, these three are somehow similar to this track, because he runs this trajectory, so in the next time step he may be here, or maybe here. It's all plausible. But also we take into account the appearance of the player. And in terms of the appearance, okay, only this one is similar to the track, because we've got the white guy running, and there is only one white. Here is not so obvious, because here we've got the player running this trajectory. More likely it will be this one, because it's closer to the previous position, and maybe, taking into account that he moves at the similar speed and with the similar acceleration, he likely will be here, but it's possible that he will be here. In terms of appearance, well, both are quite similar, so we are not sure. And there can be much complex situation. So how to address this in systematic way? Basically, here we employed deep networks to learn the features of the track and to learn these multi-Q, multimodal features to compute, assess similarity between the track and the detection. Actually, this is based on the idea from this paper, which explains details of this process. But it basically works like that we use recurrent neural network to first encode the track of the player, taking into account how his speed changes between consecutive time steps, and we take into account the features connected with the track. And these features are based basically of appearance of the player through each time step. We encode this using recurrent neural networks, and then combine both these motion-based features and appearance-based features, and use the fully connected network to compute the similarity between these encoded features from the track and each detection. So we compute similarity between this track and each detection, between this track and each detection, this track and each detection. And we've got similarity. We've got a bipartite graph with the similarities between tracks and detections, like here are the numbers. And now the task is to join and to merge tracks with detections to maximize the overall similarity. And this is a classical algorithm used for this. It's called Hungarian algorithm. It's a very efficient algorithm basically to match elements through two bipartite graphs to maximize some measure. I won't go into details of these components. They are based basically on this publication, but it looks like that to encode the player appearance, we just take the player bounding boxes from previous detections, pass from CNN convolutional network to compute features first, and then pass the resultant features through recurrent network to compute a combined description, to combined embedding that describes the player appearance. And then we use fully connected network to compare this with the player appearance in the next time step. And similarly with the player motion. Okay, I think I'm running out of time, so I will stop at this moment. So are there any questions?
Thanks for your speech. I have a question that have you tried to connect somehow the videos from the different CCTV cameras? Because you told that one camera is only a part of the playing court. So maybe you should connect the video from the other cameras to have look at the whole the court.
Yeah, we take this into account because in the basic setup we've got like 4 cameras and 4 corners. There are 2 cameras looking at each side, and then we actually, when we've got detections, we project them onto the pitch, onto the plane, because the cameras are calibrated, so we can transfer coordinates from the, let's say, camera point of view to the world coordinate system, and we project them onto the common plane, common ground, I would say. This is also used for 3D ball position recovery, because then detecting the ball from 2 cameras, we can triangulate the ball position, and then we can compute if the ball, we can compute the 3D ball coordinates. So is the ball on the ground, or is this, kicked above?
I know that you haven't mentioned that part, but is the concept of determining if something is a pass, shot, or let's say a slide is also based on the manually labeled data set? Or do you have some kind of logic that you apply?
Let's say there are 2 approaches. One is to use some simple heuristic, I would say, because we can track, if we track the ball and we can track the player, we can see if the ball has the contact with the player, if this change the trajectory, for example, and we can, based on this simple heuristic, we can classify if this was a pass, for example. Or actually, heuristic to detect if there was a goal is kind of a backward, because we can detect if the ball was placed in the middle of the playing field, and this means that it had to be, a goal area when the ball is taken. But we also experiment with the machine learning-based approach, but it's still kind of experimental.
What about foul? If someone fouls or just touches?
It's interesting, but at the moment, we do not consider this. Possibly, I think it could be with the manual labeled data, because you need a couple of examples when the 2 people one people is lying on the ground. There's a high chance that something happened, but you cannot classify, from this resolution images, you cannot tell if this was a fall or someone just stumbled against his own feet and fell down.
Do you consider joining other sources of information to your visual data analysis, like GPS trackers?
Mm-hmm. There were some experimental GPS trackers. They are used now for to keep track of the player's performance. I mean, how fast he runs and what the distance he runs. But the spatial resolution for the subjects that frequently change the direction or do the sudden movements is not sufficient. You've got like then, I don't know, a couple of meters. It looks better when the GPS is using the car, because someone use the algorithm to somehow smoother the path. You know that the car is not, jumping, So you can interpolate and smoother the path, and it's quite accurate. But for the subject that change the position very frequently and very quickly, it's not accurate. It's like, I don't know, 5, maybe 10 meters accuracy. So it's not sufficient to establish. It may help with, I don't know, maybe with tracking a little bit, but it's not sufficient to tell if someone has a contact with a ball or not.
Did you try to use less than 4 cameras to 3D track?
I mean, 2 are necessary. I haven't tried this. I've read one paper that someone used one camera to establish 3D position of the ball, doing trajectory analysis, because if the ball goes like, parabola movement, it means it has to be kicked up and down. Or maybe someone, do this trick and kick the ball, give the rotation, and it spins on the ground, but goes like parabola. So, but usually the parabola, the parabolic trajectory indicates that's in the air. But we haven't tried this.
And did you try to use pose estimation? Did you try to use pose estimation?
Yeah. There were some experiments with this. Yeah, we let's say in the production system we have such functionality.
And for players, do you use only 2D tracking or also try to track jumps in 3D trajectories for players?
No, for players we only do 2D. Because with 3D is, very infrequent, so we assume they are on the playing ground. Okay, sometimes someone can jump and play with the head, but okay, it will be some error then in position estimation, but we say accept it.
Thank you.
You said you have some problems with the ball recognition because of the field. Like there's a dot on the field that looks like a ball. Have you tried to filter out the field?
I would say in production system we've got certain post-processing steps, basically then clean these results, and this is one of them, to just filter the field out, so to only then focus on the detection within the play field. Yeah, that's one of the steps. Because as you've seen, there were a couple of false detections, like the ball is detected where the player feet is, and so this needs to be. And also sometimes you've got like spare balls lying near the playing field, especially in the training games, so this all must be filtered out.
But you did it on the after the recognition, the post-process, not before.
We do it after recognition because, sometimes when you've got like ball that's kicked outside the playing field, we don't want to lose it immediately because sometimes it's kicked outside and we want at least to keep track of it, at least to see that, that it goes outside, to see the trajectory. So we don't want to rigorously cut out the field.
Okay, thank you.
Thanks. You mentioned detecting the player numbers from the jerseys. So how well does that actually work? And can you, for example, track player statistics over the whole football game?
Well, in practice, it depends on the resolution of videos. With these videos, it's extremely difficult to recognize by jersey numbers. So in the setup, when you've got more cameras, like maybe 6 cameras, 2 additional cameras at the side of the field, then you can detect jersey numbers better, I would say.
Okay, thanks.
Could you repeat what's the size of your data set and how diverse is it? How many films, labeled films you have, and do you have only professional players or as well some amateurs in some unprofessional?
Let's say for our purpose, we use the data set that got about 8,000 frames from different matches, from different playing fields to provide the diversity. And these were matches by the professional football clubs.
So in total, it's like a few minutes of video?
But it was not a consecutive, yeah, because in the consecutive video, usually we've got the same lighting, the same jersey colors, so we would like to provide diversity. So it were just selected frames from a number of matches to provide the diversity. Because if we train this on 8,000 frames from one match, and then they, wear different jerseys, it will fail very likely because it haven't seen guys. If, for example, there were different lighting conditions, it will also very likely fail. So the diversity of the data is key.
Thank you.
I guess this is all questions. Thank you very much.
Thank you.